Friends, very good morning. We were dealing with the retrosynthetic strategy for the synthesis of various organic compounds. Today's subject of discussion is ring synthesis, means the cyclic organic compounds. Right? The rings can be 3 membered, 4 membered, 5 or 6 membered, which are generally utilized. The rings may be carbocyclic ring system or an heterocyclic ring system. Today's subject of discussion is three-membered ring synthesis, the retrosynthetic strategy. What strategy we follow to synthesize a three-membered ring system, which may be a heterocyclic or a carbocyclic ring system. Generally, the heterocyclic ring system is an epoxide. How that is the strategy we follow to synthesize these epoxides. General strategy we follow is I'll break over here at the heterojunction. CX disconnection. This is 1 comma 1 difunctionalized derivative, and I disconnect over here 1 comma 1 disconnection, and if I add oxygen across this carbon carbon bond, I'll get an epoxide, a three-membered ring system. This is the one strategy. Another strategy is I'll break upon this at this position over here. If I break over here, this part will become one synthon and this part will become another synthon. If I break over here, I'll get, to add oxygen, I create a double bond over here. I'll get corresponding alpha beta unsaturated ester as one of the reagents. If I carry out epoxidation of this alpha beta unsaturated position, I'll get corresponding epoxide. If I break over here at the this junction, this part, this synthon CH3CO, this part will be an acetone. Another part which I have broken, it has a negative charge over here. These synthons can be, this is electron rich, it attacks on carbonyl carbon, pi electrons moves OH, and then cyclization occurs, I'll get epoxide. Two approaches are followed. One mechanism involves epoxidation of alpha beta unsaturated ester. Another approach is the ring closure of reacting acetone with this synthon. How can we approach this? Epoxidation. To do epoxidation, I treat this alpha beta unsaturated ester with hydrogen peroxide and a base. I'll get corresponding epoxide. Another strategy, the second one is I attach an electron withdrawing group at this position. I'll get corresponding chloroethyl acetate. And I treat this chloroethyl acetate in the presence of a strong base like sodium ethoxide. At the acetone, I'll get ring closure reaction to give the same epoxide. Let us look into the mechanism of the reaction. The first one is epoxidation. I have taken hydrogen peroxide and treated with a base. Hydrogen peroxide is HOOH. When I treat with a base like sodium hydroxide OH minus is electron rich. It acts as a nucleophile. It abstracts the proton from this HOOH. When the proton is abstracted, the excess electrons are left onto the oxygen and proton leaves, leaving the electrons onto the oxygen to give rise to the oxygen which is rich in electrons. This peroxide ion can react with alpha beta unsaturated ester. This excess electron and this alpha beta unsaturated ester, the excess electrons attacks on the carbon. Once this attacks on this carbon, it has to maintain its stability. The pi electrons moves on to the next carbon and it has to maintain its tetravalency. Hence, the pi electrons are kicked off onto the oxygen and I will get O minus and this combines with H plus to give OH. Again, when I heat it strongly, the OH bond breaks and these electrons are used to form double bond with the adjacent carbon. As it has to maintain its tetravalency, this excess electrons moves on to the adjacent carbon and that attacks on this oxygen and OH gets kicked off. I got epoxide with loss of water molecule. Another approach is take chloroethyl acetate, treat with a base like sodium ethoxide O minus, abstract hydrogen and the excess electrons are left onto the carbon giving rise to a carbene ion and this carbene ion which is formed reacts with acetone. The carbonyl carbon of the acetone is the electron deficient center which is attributed to the electronegativity of the oxygen. This is electron rich and this is electron deficient. Unlike poles attract each other, minus attacks on the positive carbonyl carbon. Excess pi electrons moves onto the oxygen and becomes OH. Again, oxygen in OH has lone pair of electrons that is donated to this electron deficient center. This electron deficient carbon, because it is flanked between the carbonyl and the halogen group, both are electron withdrawing. It withdraws electrons and renders this carbon positive center. Electron deficient. Is electron deficient, is electron rich, cyclization occurs and it has to maintain its tetravalency. Halogen is an easy leaving group, that's why it gets kicked off and I lose HCl and I get an epoxide. This is a strategy which I am using to synthesize a three-membered heterocyclic ring system, that is an epoxide. Let us look into three-membered ring system which is carbocyclic in nature. It is not heterocyclic. All the three are carbon itself. Which strategy I can follow? I break up this molecule over here. This, when I break up, the electrons are taken away from this carbon and it becomes electron rich carbene ion and these excess electrons are shared with the adjacent carbonyl group. That's why it becomes stabilized. Once these electrons are taken away from here and this becomes electron deficient CH2 plus. To get CH2 plus I add a electron withdrawing group over here, and I get the reagent by disconnecting this to give this molecule. When I treat with the base, this is adjacent to carbonyl group. This is electron deficient due to the electron withdrawing group which is adjacent to this carbon. That's why it is acidic enough to lose the proton, this carbon. In the presence of the strong base, this excess electrons take away the proton, creating a carbon ion, and this carbon ion attack on this positive center. This is positive because there is an electron withdrawing group adjacent to this. Cyclization occurs. I get a carbocyclic ring system. This is the strategy which we follow for a three-membered ring having carbocyclic system. If I want to get this molecule directly, I cannot get. I do fragment group interconversion. This bromine I replace with OH. Then I break upon over here. Once I break upon over here, this becomes electron rich and this become electron deficient. Disconnection. This is positive center. This is oxygen. O minus combines with this positive center. I get an epoxide and I have corresponding CH2COR. To this I added ester. I treat with a base the electrons deficient center because this is flanked between two carbonyl groups. When I treat with a base, it is acidic enough to lose the proton, giving rise to carbon ion. Carbon ion attacks on this carbon and the ring opening occurs. I'll get this molecule and then treat with base again. This I do fragment group interconversion. I brominate this and I treat with a base. I'll get the carbocyclic ring system. We have discussed about a three-membered ring system synthesis having carbocyclic ring system and heterocyclic ring system. In the next class, we deal with the ring system containing 4 carbons, 5 and 6 carbons respectively. Till then, have a nice day. Thank you. Ultimately, we follow two strategies. For heterocyclic ring system, we follow epoxidation or ring closure. For carbocyclic ring system, I break the molecule and I will get a positive and negative center, and I also carry out ring cyclization. These are the two strategies which we follow for three-membered ring system. Next class we will deal with others. Till then, have a nice day. Thank you.